Making stuff look good with Unity.
Hello and welcome to another episode of Making Stuff Look Good in Unity. Today we'll be doing another visual case study, this time taking a look at the Ice Caverns level in Spelunky. As if being an incredibly well-designed game wasn't enough, Spelunky is filled to the brim with beautiful visual effects, dynamic lighting, juicy blood particles, and those shimmering gemstones to name a few. But there's one effect in particular that has caught my eye. Icy crystal formations in the background of the Ice Caves levels have these awesome distorted reflections. It's a pretty subtle effect that you might not even notice. This is especially true when you're under the pressure of having a regular run that makes it past the jungle. The effect actually seems underutilized to me given how fantastic it looks, but I can understand that they didn't want to compromise the player's ability to read the environment by refracting light and objects all over the place. Here's my recreation. It's by no means a one-to-one recreation, but the shader at work could probably do so if I were a talented enough artist to draw the sprites as they look in Spelunky. Okay, so let's jump into how we can achieve this effect. We'll create a big old ice cube to keep things simple, because creating the art assets for a more complex crystal formation is much trickier and would require some Photoshop teaching that I'm not going to get into for now. Now the way I see it, there are three key components to the effect. 1. It reflects all of the foreground sprites. When I say reflect, I really mean redraws them offset and a bit larger. For instance, we see the front of Spelunky guy's face in the reflection and not the back of his head. 2. It distorts the reflection to match the shape of the crystal sprite. And 3. The crystal looks slightly different based on the camera's position. The ice should shimmer as the player moves about, even if nothing is being reflected in it. We'll get right into step 1, creating the reflection. This is probably the most interesting part of the effect. To achieve this, we'll use a multi-camera setup. This is something I haven't done in any of my videos to date, but knowledge of multi-camera setups is an essential tool to have on your technical artist tool belt. We'll attach a second camera as a child of our main camera and set its culling mask to a custom layer called Reflectables. We disable all the other masks so that this camera only renders objects on the Reflectables layer. Now we don't want our Reflectables being drawn to the screen, instead we want them to output to a render texture we can use in our shader. You could actually create a render texture in your assets folder, but I prefer to create one in code, that way we can dynamically size it to match the screen and whatnot. Here's a chunk of the script we'll put on the reflection capturing camera. The generate RT method is where most of the magic happens. We start by grabbing a reference to the camera. We'll check its target texture, and if it's already set to something, we'll destroy it before we create a new one. This just avoids a memory leak in the editor. Now we new up a render texture. I also take this opportunity to downres the texture to give it a bit of a blur, as we did with our box blurs in Shaders 102. We'll set the filter mode to bilinear, because point sampling would give our reflections chunky pixels when it's downresed. And finally, we'll set a global texture to use in our shader. This last line is pretty cool. Usually our image effects are creating temporary render textures and blending them to the screen every single frame. But what we'll do here is give all shaders a global reference to the render texture. This only needs to be set once when the texture is created. From that point on, whatever the camera renders will be accessible from shader. Wicked. Back in our scene, we'll set the player, the ground, and some snow particles to the reflectable layer. Now we can preview our render texture by double-clicking the target texture field in the camera's inspector. Don't worry about the choppy playback in the preview, it's actually capturing at the same frame rate as the rest of the game. A quick note while we're here, you can hit this toggle to see the alpha channel of the render texture. The background in mine is entirely black here because I used a color with an alpha value of 0 for my solid clear. This will matter more in a little while. Okay, so now we've got everything we want reflected available to the shader, so it's time to write a shader. We'll start off with a pretty standard take on a sprite shader. I actually used the one I wrote for Shaders 101 as a base. Here are the structs for passing data through the shader. Our shader will expect positions, UVs, and vertex colors from the mesh. I haven't talked about vertex colors in the past, so let's go over how they work here. Data coming from the mesh will always include, at the very least, the positions of the vertices. But it can include other things as well. For instance, we've used the UV data before for texturing a sprite. Another common bit of data each vertex can send along is a color. The sprite renderer, for example, sets the color of each vertex to the sprite color you set in the inspector. This way, we can use the vertex color to tint the sprite on a per object basis, rather than having to make a new material for every single sprite we want to have a different tint. Moving on, our v2f struct carries the position, text coord, and color along, but also tacks on an additional text coord called screen UV. This will be the position of the fragment on the screen. That's also the most interesting portion of our vertex program, so let's check it out. I'm totally going to gloss over some technical stuff here, but if you want a better understanding, look into how homogeneous coordinate systems work. It's basically a 4-dimensional hack for 3D transformations. After our vertex position has been multiplied by the MVP matrix, it's in what's called clip space. We'll take the XY component of the clip space coordinates and divide out the W component. This step is actually only necessary for our perspective projection camera. When using an orthographic projection, W just equals 1. Now we have a point in what's called the normalized device coordinates, or NDC. These values range from -1 to 1, but we want them in the range 0 to 1 for use with texture sampling. So we just add 1 and half the result. And finally, we can produce a reflection in our fragment shader. We'll ignore all the other texture and color data for now, and just return a color which will sample from our global refraction text at the point of our fancy screen UV coordinate. Back in our scene, we'll toss this shader on a material and apply this material to the ice cube sprite. Now, when we run our scene, what gives? No reflections. Wait, our reflections are in the exact same position as the objects they're reflecting, so let's move our reflection camera a little bit. Nice, now we can see our Spelunky guy reflected on the invisible ice cube. We can also decrease the orthographic size of the reflection camera to make the reflected image larger. We'll bring in the texture and vertex coloring of the source sprite and then perform a little alpha blend with our reflection. Now our ice cube isn't invisible, and we can tint our ice cube with the sprite's color. You could optionally also tint the reflected image by the vertex color as well. And with that, we're done the first major component of the effect. Now let's move on to the next part, the distortions. Light seems to bounce around every which way in Spelunky's ice crystals. I'm all but positive this is achieved using some variation of a normal map. I talked about using the red-green values of a texture to encode sampling offsets in Shaders 102, and that's exactly what we'll do here. This is the normal map I'll be using for refracting light off the ice cube. I'm actually not using the blue channel for anything meaningful, but I left it at 1 because this is what most people are used to a normal map looking like. You could probably use the blue to encode the strength of the reflection if you wanted to get really fancy. Back in our shader, we'll sample the normal map and grab the XY components. These can also be referred to as the RG components, either swizzle will work. These numbers are in the range 0 to 1, but we want them from -1 to 1, so we'll adjust for that. Now, when we sample world reflections, we'll include our offset value. Let's check out what that looks like in our scene. The edges look a bit extreme, but we're sampling from a texture in the range 0 to 1. Offsetting by values as large as -1 or 1 has a significant impact. What we'll do to compensate is we'll multiply the offset by some magnitude. We'll just hard-code a really small number for now. Okay, this looks much better, but before we get too excited, we need to check out another small issue. When we rotate the ice cube around, it looks a bit strange, especially at 180 degrees. This is because our normals are in local object space. Here, we'll visualize what the X offsets look like. The more blue a pixel is, the more it offsets from the left. The more red, the more it offsets from the right. When we flip the ice cube upside down, the red and blue flip as well, so the right side is now sampling from the left and the left side is sampling from the right, and this is what makes it look so peculiar. To fix this, we have to account for the object's transformation into world coordinates. We can do this with a matrix multiplication using the object to world matrix. Now if we visualize the offsets, you'll see that the left side remains blue and the right side stays red as we rotate the object. And switching back to our reflections, everything is now looking nice with no weird stretching or distorting. Our shader is coming along nicely. At this point, let's take a moment to parameterize two things, the magnitude of the refraction and the visibility. These will both be global uniforms we can set through the camera script we wrote earlier, and we'll use them in the shader to eliminate magic numbers. I find turning down the visibility to 50% lets through enough of the blue color while still maintaining a nice reflection. This is also a good time to point out a little quirk in our shader. When the same material is used on objects, Unity will attempt to batch them dynamically. Unfortunately, the object to world matrix is set to the identity matrix when objects are batched, so our attempt to correct the normals will be nullified. Luckily, you can add the disable batch equals true tag to your subshader tags to force objects not to batch. If you want to have thousands of reflecting objects, you'll either have to put up with the incorrect normals or suffer the draw calls. In this case, I'm going to go with the draw calls. The third aspect we'll attempt to recreate is that the crystals are view dependent. As the camera moves, they seem to dynamically reflect something. I kept this relatively simple by having them sample the same texture I used for the background and distorted as we did the other refractions. I left some magic numbers in here that I wasn't sure how I wanted to parameterize that boost the refraction magnitude and control the tiling of the background tile. This could be better, but I'm happy with the way these look for the final product, so we'll leave them for now. We'll take this ambient color and add it to the base color. Disabling reflections, we can see that the ice cube now has some extra details that make it appear a bit different depending on where the camera is. This effect is particularly noticeable with a more complex normal map like I have on these crystals. Here's an example of what a more complex normal map would look like. It has a lot of edges and a dimpled surface to get the most out of our shader. Like I said, the finished product isn't one-to-one with Spelunky's, but with the right maps and color scheme in the base art assets, this shader could get very close. And that's all she wrote. Sorry if this episode feels too information dense. I always bite off more than I can chew, especially when targeting a 10-minute video length. As usual, I'll include a link in the description to where you can download the shaders and scripts used in this video. Special thanks goes out to this week's Patreon subscribers. You guys are the best. And as always, thank you all for watching. Keep on making those video games.